The planet Mars is not what you think. Almost everything you were taught in school about the red planet is incomplete. We imagine Mars as a dead world, a frozen desert of rust-colored rocks and ancient craters, a place where nothing moves and nothing changes. But Mars is not dead. It's just very good at keeping secrets. This is the story of what we actually found when we started looking closer, and it begins with something as simple as color. When you look at Mars through a telescope from Earth, you see a pale orange dot, a cinder floating in the darkness. We've been calling it the red planet for thousands of years. The Egyptians called it Herdesha, the red one. The Romans named it Mars, after their god of war, because its reddish glow reminded them of blood. But here's the first thing most people get wrong about Mars. It's not actually red. When NASA's Viking landers touched down on the Martian surface in 1976, they sent back the first color photographs ever taken from the ground. The images broadcast on television showed a blue sky, Earth-like, familiar. But within hours, NASA corrected the images. The sky wasn't blue, it was pink. Butterscotch, actually. The true color of Mars, from the surface, is more like a desert at sunset, golden browns, tans, and a dusty orange haze hanging in the air. The redness we see from Earth is just a thin layer of iron oxide dust, typically only millimeters thick. Even in places like the Tharsis region, where the dust is thickest, it's probably no more than 2 meters deep. Mars isn't red. Mars is rusty, and that rust is skin deep. Let's start with the sky. On Earth, we have blue skies because our atmosphere scatters blue light more than any other wavelength. It's called Rayleigh scattering, and it happens when sunlight hits molecules of nitrogen and oxygen. The blue light bounces around in all directions, painting the sky. Mars has almost no atmosphere. The volume of gas surrounding the planet is less than 1% of Earth's. It's so thin that liquid water can't exist on the surface for more than a few seconds before it either freezes or evaporates. The atmospheric pressure is too low. But Mars does have a sky, and that sky is butterscotch. The color comes from dust, fine particles of iron-rich minerals, between 3 and 45 micrometers in diameter, suspended permanently in the Martian atmosphere. These particles absorb blue light and scatter red and yellow wavelengths instead. The result is that warm, dusty tone that dominates the daytime sky. But here's where it gets strange. At sunset on Mars, the process reverses. As the sun drops toward the horizon, a blue haze gathers around it, the complete opposite of Earth's pattern. On Earth, sunsets glow orange and red. On Mars, sunsets glow blue. This happens because of something called me scattering. When sunlight passes through the dust at a low angle during sunset, the fine particles scatter blue light forward, directly toward the sun's position. The rest of the sky stays its usual butterscotch color, but around the sun itself, you'd see a pale blue glow. It's backwards, inverted, like looking at Earth through a mirror, and the sun itself looks smaller from Mars, only about 2/3 the size you're used to seeing from Earth. That's because Mars orbits about 80 million kilometers farther from the sun than we do. So if you were standing on the surface of Mars at dusk, you'd see a smaller sun setting into a dusty orange sky, surrounded by a faint blue corona. The landscape around you would be painted in shades of gold and brown, and the air would be cold, brutally cold. At the equator, at noon, the temperature might reach 20 degrees Celsius at your feet, but at your head, it would still be below freezing. The atmosphere is so thin that heat escapes almost instantly. This is Mars, a world of inversions and contradictions, and we're just getting started. For most of human history, we thought Mars was dry, bone dry, a desert world where water had vanished billions of years ago, if it had ever existed at all. Then we found the evidence. NASA's Mariner 4 spacecraft flew past Mars in July 1965 and sent back the first close-up photographs of another planet. This picture showed craters, lots of craters, a barren, cratered landscape that looked more like the moon than anything on Earth. Scientists at the time were profoundly disappointed. They had expected to see canals, or at least some sign of geological activity. Instead, they saw a dead world, untouched for billions of years. But they were looking in the wrong place. As more spacecraft arrived at Mars over the following decades, a different picture emerged. Networks of valleys carved into the surface, ancient riverbeds that merged into larger channels, deltas, where rivers once emptied into basins that could have been lakes or seas, features that could only have been shaped by flowing water. Mars had been wet, very wet. In 2008, NASA's Phoenix lander touched down near the Martian North Pole and dug into the regolith, the loose, powdery soil covering the surface. It found water ice just beneath the surface, lots of it. In some regions, the regolith contains up to 5% water by weight. Then in 2013, NASA's Curiosity rover drilled into the soil at Gale Crater and found something remarkable. The sample contained between 1.5 and 3% water by weight, easily accessible water, bound up in the minerals themselves. Heat the soil, and the water evaporates out. In 2015, scientists using NASA's Mars Reconnaissance Orbiter observed dark streaks appearing on slopes during the Martian summer. The streaks grew and faded with the seasons. Analysis suggested they were caused by briny water, salty enough to remain liquid even in the cold Martian temperatures. And in 2019, researchers reported evidence of ancient tsunamis. Two massive waves, each about 50 meters high on average, swept across a northern ocean billions of years ago. The waves were triggered by asteroid impacts that created craters 30 kilometers wide. The backwash from these tsunamis rearranged boulders the size of cars and left behind channels carved by retreating water. All of this points to the same conclusion. Mars once had an ocean, a vast body of water covering nearly a third of the planet's surface, filling the low-lying basin in the northern hemisphere. Scientists call it Oceanus Borealis, the Northern Ocean. It would have been huge, about the size of Earth's Arctic Ocean, deep enough to submerge features we now see as ancient shorelines. And it existed for millions of years, perhaps longer. But then it disappeared. The existence of liquid water on Mars requires two things: a thicker atmosphere and a warmer climate. Today, Mars has neither. The atmospheric pressure on Mars averages about 600 pascals. That's less than 1% of Earth's sea level pressure. At that pressure, water can't remain liquid. It either freezes solid or boils away almost instantly, depending on the temperature. The average surface temperature on Mars is around -63 degrees Celsius. In the coldest regions, it drops to -153 degrees. That's cold enough to freeze carbon dioxide out of the air. So if Mars once had oceans and rivers, it must have had a much thicker atmosphere, something that could trap heat and keep water liquid. Early Mars probably had a carbon dioxide atmosphere similar in thickness to present-day Earth, about 1,000 hectopascals. With enough greenhouse warming, possibly boosted by methane or insulating carbon dioxide ice clouds, the surface temperature could have been warm enough for liquid water. But that atmosphere is gone now, and we know what happened to it. Mars used to have a global magnetic field, generated by convection currents of molten metal in its core. This magnetic field acted as a shield, deflecting the solar wind, the stream of charged particles constantly flowing out from the sun. But about 4 billion years ago, Mars cooled. The convection in its core stopped. The magnetic field collapsed. Without that shield, the solar wind hit the Martian atmosphere directly. And over the next few 100 million years, it stripped most of the atmosphere away into space. NASA's MAVEN spacecraft, which arrived at Mars in 2013, measured the current rate of atmospheric loss. The solar wind is stripping away gas at a rate of about 100 grams per second. That doesn't sound like much, but it adds up. MAVEN also observed what happens during solar storms. When a wave of high-energy particles from the sun hits Mars, the atmospheric erosion rate increases dramatically. And in the early solar system, when the sun was younger and more active, solar storms were far more frequent and powerful. The loss was catastrophic. Over a few 100 million years, Mars lost most of its atmosphere. Without the greenhouse effect, the planet froze. The oceans evaporated or froze and then sublimated away into space. Rivers stopped flowing. The water cycle shut down. Some of the water remains, locked in ice beneath the surface. Some of it exists as hydrated minerals in the rocks, but most of it is gone. And Mars became the cold, dry world we see today. In June 2008, NASA's Phoenix lander performed a simple chemistry experiment. It scooped up a sample of Martian soil, mixed it with water brought from Earth, and measured the pH. The result was 8.3, slightly alkaline, similar to the soil in a backyard garden on Earth. The scientists were excited. The soil contained magnesium, sodium, potassium, and chloride, all nutrients that plants need to grow. One researcher compared it to the dirt in his own garden and said it could probably support plant life. But then they found something else: perchlorate. Perchlorates are salts containing chlorine and oxygen. On Earth, they're rare and usually occur in very dry environments. But on Mars, they're everywhere. Phoenix measured perchlorate concentrations of about 0.5% in the soil. That's high enough to be toxic to humans. Every subsequent mission to Mars has confirmed the presence of perchlorates. NASA's Curiosity rover found them at Gale Crater in 2012. The Mars Odyssey orbiter detected them globally across the entire planet. They're in the soil, in the dust, and probably in the ice. Perchlorates interfere with thyroid function in humans. They prevent the thyroid gland from absorbing iodine, which disrupts hormone production. Long-term exposure causes serious health problems. They're also toxic to plants. Studies on Earth show that perchlorates reduce chlorophyll production, shrink root systems, and stunt growth. At concentrations above 0.5 grams per liter, which is roughly what you'd find in Martian soil, most plants die. There's another problem. The high levels of ultraviolet radiation reaching the Martian surface break down perchlorate molecules, creating even more dangerous chemicals. Laboratory tests on Earth show that these UV-generated compounds are more lethal to bacteria than the perchlorates alone. So the Martian soil isn't just toxic, it's becoming more toxic over time. This presents a significant challenge for future human exploration. Martian dust is fine, much finer than sand, and it gets everywhere. It clings to surfaces through electrostatic charge. The Mars Pathfinder rover in 1999 detected dust accumulating on its wheels simply from rolling across the surface. When astronauts return to a habitat after working outside, they'll bring that dust with them. Even with careful decontamination procedures, some will get inside. And because the dust particles are so small, they can be inhaled. The perchlorates aren't the only concern. A 2002 study warned that Martian dust might contain highly reactive silicate minerals, olivine, pyroxene, and feldspar, that produce dangerous molecules when exposed to small amounts of water. These molecules are similar to compounds that cause lung disease in miners on Earth, including cancer. NASA's Mars Exploration Program has been studying these hazards for more than 2 decades, but the instruments sent to Mars so far haven't been designed to measure the specific carcinogens that are of concern. The Mars 2020 Perseverance rover carries instruments that will help answer some of these questions. MEDA measures atmospheric properties, including radiation and dust size. Pixel and Sherlock analyze the elemental and mineralogical composition of surface materials at a very fine scale. Eventually, samples from Mars will be returned to Earth for detailed laboratory analysis. Only then will we fully understand the risks. But for now, the message is clear. The Martian environment is hostile. Not just cold and airless, but chemically hazardous in ways we're only beginning to understand. So why is Mars covered in iron oxide dust? Why is everything rust-colored? The answer is surprisingly complex. Rust forms on Earth when iron reacts with oxygen and water. You need all three: iron from the rock, oxygen from the air, and water to facilitate the chemical reaction. But Mars has almost no free oxygen in its atmosphere. Atmospheric modeling suggests the partial pressure of oxygen on Mars has never exceeded 0.1 micropascals over geological time. That's essentially zero. So how did all that iron get oxidized? There are several possibilities, and all of them could be happening at once. One process involves a direct chemical reaction between iron and water. When water comes into contact with iron-containing minerals, it can oxidize the iron without any free oxygen being present. The hydrogen atoms in water molecules strip electrons away from iron atoms, leaving behind oxidized iron-ferric iron, which forms minerals like goethite. This reaction is thermodynamically unfavorable under normal conditions, but it can be sustained if the hydrogen gas produced by the reaction escapes quickly into the atmosphere. On Mars, with its thin atmosphere and low gravity, hydrogen escapes easily. The reaction can be enhanced by dissolved carbon dioxide and sulfur dioxide, which lower the pH of any briny films that might form on rock surfaces. Lower pH means more hydrogen ions, which makes the oxidation process more efficient. Another process involves hydrogen peroxide. Even though hydrogen peroxide is very rare in the Martian atmosphere, it's a much stronger oxidizing agent than water. Laboratory experiments show that hydrogen peroxide can oxidize iron minerals efficiently, producing the same ferric oxides we see in Martian dust. There's also evidence that mechanical erosion plays a role. Experiments at the Mars Simulation Laboratory in Denmark show that when a mixture of magnetite powder and quartz dust is tumbled together, some of the magnetite converts to hematite, the red iron oxide that gives Mars its color. The mechanism is fascinating. When quartz fractures during grinding, chemical bonds break at the newly exposed surfaces. When those surfaces come into contact with magnetite, oxygen atoms transfer from the quartz to the magnetite, forming hematite. This means that wind-blown dust storms on Mars, which are frequent and can last for months, might be continuously producing more rust simply through the mechanical grinding of rocks against each other. All of these processes have been occurring for billions of years. The result is a planet where nearly every exposed surface has a thin coating of iron oxide dust. And because there's no liquid water to wash that dust away, and no vegetation to stabilize it, the dust just sits there, waiting to be stirred up by the next windstorm. The dust is so pervasive that it even colors the sky. Suspended particles absorb sunlight in the blue-green wavelengths and scatter red and yellow light, giving the Martian sky its characteristic butterscotch hue. It's worth noting that this reddish dust is only a surface feature. Beneath it, Mars is made of basaltic rock, dark gray and black, similar to volcanic rock on Earth. The red planet is really a gray planet with a thin red coating, but that coating tells a story. It's evidence of billions of years of chemical weathering, of an atmosphere that once held moisture, of a planet that was once very different from what we see today. In 2017, NASA's Curiosity rover made a disturbing discovery in Gale Crater. Curiosity had been studying layers of mudstone, ancient sediment deposited at the bottom of a lake billions of years ago. These layers should have been rich in clay minerals, which form in the presence of water and preserve a chemical record of environmental conditions. But in some locations, about half the clay minerals were missing. Instead of clays, Curiosity found mudstones rich in iron oxides, the same rusty minerals that give Mars its red color. The samples were from the same geological layer. They were the same age. They started out identical, but in some places, the clays had been replaced by iron oxides. The rock record had been altered. The culprit was brine. Super salty water, much saltier than seawater on Earth, had seeped down through cracks in the overlying rock layers long after the mudstones formed. This briny groundwater dissolved the clay minerals and redeposited iron oxides in their place. The process is called diagenesis. It's a kind of chemical rewriting that happens underground when water moves through rocks, dissolving some minerals and precipitating others. Diagenesis creates an underground environment that can actually support microbial life. Some of the most extreme habitats on Earth, places where bacteria thrive deep beneath the surface, far from sunlight, are powered by diagenetic processes. But diagenesis also erases evidence. Clay minerals are like time capsules. They preserve a record of the water chemistry, temperature, and pH when they formed. They can even preserve organic molecules, the chemical signatures of life. When diagenesis replaces clays with iron oxides, that record is lost. The evidence disappears. This is a problem for the search for ancient life on Mars. We know that Gale Crater once held a lake. We know that the environment was potentially habitable. But in some places, the evidence of what actually happened in that lake has been chemically erased and overwritten. The good news is that we now know this happens. We can identify which rocks have been altered and which haven't. By comparing mineral compositions across different areas, we can map out where the rock record is pristine and where it's been compromised. This information will be crucial for NASA's Mars Sample Return mission. The Perseverance rover is currently collecting samples from Jezero Crater, another ancient lakebed. Those samples will eventually be brought back to Earth for analysis in laboratories far more sophisticated than anything we can send to Mars. But the researchers will need to be selective. Not all Martian rocks are equally good at preserving evidence. Some have been chemically reset. Others remain untouched, holding secrets from billions of years ago. The challenge is knowing which is which. In April 2025, scientists analyzing data from NASA's InSight lander made an extraordinary announcement. There is liquid water on Mars. A lot of it. Not on the surface, that's impossible given the current atmospheric pressure and temperature. But deep underground, between 5.5 and 8 kilometers beneath the surface, seismic data suggests the presence of a layer of liquid water trapped in fractured igneous rocks. The total volume could be enormous, enough to flood the entire Martian surface with an ocean 520 to 780 meters deep, about the same volume of liquid water contained in Antarctica's ice sheets. The discovery was made by analyzing recordings of marsquakes, seismic events, detected by InSight seismometer over nearly 4 years of operation. When seismic waves travel through rock, they change speed, depending on what the rock contains. Waves travel differently through dry rock, ice-filled rock, and water-filled rock. By studying the arrival times and characteristics of seismic waves from more than 1,300 marsquakes, researchers were able to infer the properties of the rocks deep beneath the surface. The data strongly suggests the presence of liquid water in pore spaces and fractures within the mid-crust. This water isn't drinkable. It's probably extremely briny, filled with dissolved salts and minerals that lower its freezing point and allow it to remain liquid despite the cold temperatures underground. But it exists, and it's been there for a long time. This has profound implications for the habitability of Mars. On Earth, microbial life exists deep underground in similar environments. These organisms live in the pore spaces of rocks, feeding on chemical energy from reactions between water and minerals. They don't need sunlight. They don't need oxygen. They just need liquid water and a source of energy. If life ever arose on Mars during its warm, wet period billions of years ago, it might have retreated underground as the surface froze. It could still be there now, thriving in the deep subsurface, completely isolated from the harsh conditions at the surface. This is speculation, of course, but it's testable speculation. Future missions to Mars could drill deep enough to sample this subsurface water. Or they could look for locations where the water migrates closer to the surface, places where geothermal heat or tectonic activity brings it within reach. The challenge is that drilling 10 to 20 kilometers into the Martian crust is far beyond our current capabilities. Even on Earth, the deepest hole ever drilled, the Kola super-deep borehole in Russia, only reached about 12 kilometers. And that took 20 years. But the discovery changes how we think about Mars. It's not a completely dead world. There's a hidden ocean down there. A dark, cold, salty ocean, trapped in rock, but an ocean nonetheless. And where there's liquid water, there's always a chance. Mars doesn't have a global magnetic field. Not anymore. But it used to. NASA's Mars Global Surveyor, which orbited Mars from 1997 to 2006, detected patches of strong magnetization in the Martian crust particularly in the southern highlands. These patches are remnants of an ancient magnetic field that existed about 4 billion years ago. We know Mars had a magnetic field because the rocks remember. When volcanic lava solidifies, magnetic minerals within the rock align themselves with the planet's magnetic field, like tiny compass needles frozen in place. Those alignments are preserved for billions of years. The magnetic signatures in Martian rocks are clear. Mars once had a strong, Earth-like magnetic field, and then it vanished. The loss of the magnetic field is directly linked to the loss of Mars's atmosphere. Earth's magnetic field deflects the solar wind, protecting our atmosphere from being stripped away. Mars, without that protection, lost its atmosphere at an accelerated rate. The question is, why did Mars lose its magnetic field? The answer has to do with the planet's interior. A magnetic field is generated by convection currents in a planet's core. For convection to occur, the core must be at least partially liquid, and there must be sufficient heat to drive circulation. Mars is smaller than Earth. It has less internal heat, and because it's smaller, it cooled faster. At some point around 4 billion years ago, Mars's interior cooled enough that convection in the core stopped. Without convection, the magnetic field collapsed. Recent findings from NASA's InSight mission confirm that Mars has a liquid outer core. Seismic data detected in 2023 revealed the presence of a solid inner core, about 613 kilometers in radius, surrounded by a liquid outer core. The inner core is relatively small and contains a high concentration of light elements: carbon, oxygen, hydrogen, and sulfur. These elements are mixed with iron, and the combination lowers the melting point of the core material. But the core isn't generating a magnetic field. It's not convecting. The temperature gradients aren't steep enough, or the composition isn't right, or both. The absence of a magnetic field has consequences beyond atmospheric loss. It also means Mars's surface is constantly bombarded by cosmic rays, high-energy particles from deep space that can damage biological molecules. On Earth, our magnetic field deflects most cosmic rays. The few that get through are absorbed by the atmosphere. But on Mars, with no magnetic field and almost no atmosphere, cosmic rays hit the surface at full strength. This makes the Martian surface even more hostile to life. Any organism exposed on the surface would be subjected to intense radiation. DNA would be torn apart. Organic molecules would degrade. If life exists on Mars today, it's underground, protected by layers of rock, living in darkness, far from the radiation-soaked surface. On the 4th of May 2022, NASA's InSight lander detected the largest marsquake ever recorded, magnitude 4.7. The seismic waves reverberated through the planet for hours. At first, scientists thought the quake had been caused by a meteorite impact. Two previous large marsquakes, magnitude 4 and 4.1, had both been traced to asteroid strikes. Fresh craters were found in locations, and at times that matched the seismic signals. So the natural assumption was that the magnitude 4.7 quake was also an impact. It even had similar characteristics: surface waves, wide frequency range, and high energy. But then researchers organized an international collaboration. 12 imaging systems operated by space agencies from NASA, ESA, the UAE, India, and China analyzed orbital data from 8 different spacecraft. They searched for signs of a fresh crater, a blast zone, or dust clouds that would indicate an impact. They found nothing. If the quake had been caused by an impact, the crater would have been enormous, probably 300 to 500 meters in diameter, with a blast zone 100 kilometers across, something that large would be impossible to miss. But it wasn't there. The conclusion was unavoidable. The quake was tectonic. It came from inside Mars itself. This is surprising because Mars doesn't have plate tectonics. Earth's crust is divided into multiple plates that move and grind against each other, generating earthquakes along fault lines. Mars has only one tectonic plate, but Mars does have internal heat. The core is still partially molten. Heat from the cooling core creates stresses in the crust as the planet contracts and flexes. those stresses build up over time until they're released suddenly in the form of marsquakes. The discovery of a magnitude 4.7 tectonic marsquake tells us that Mars is still geologically active, not as active as Earth, but not completely dormant either. InSight detected more than 1,300 marsquakes during its 4-year mission. Most were small, but some were large enough to reveal details about Mars's interior structure. One of the most significant discoveries came from analyzing a group of 3 nearly identical marsquakes called a quake triplet that occurred at the same location 9 days apart. These repeating quakes came from Cerberus Fossae, a tectonically active region about 1,640 kilometers from InSight's landing site. Repeating quakes indicate an active fault system. The same fault ruptures multiple times as stress builds and releases. On Earth, this behavior is common in seismically active zones. On Mars, it suggests that Cerberus Fossae is a region where the crust is still actively deforming. Marsquakes also helped scientists discover the solid inner core. By analyzing seismic waves that traveled through the deepest parts of the planet, researchers identified phases that reflected off the inner core boundary and transited through the inner core itself. The inner core is small, dense, and probably composed of iron mixed with light elements. Its existence tells us that Mars's core is still undergoing crystallization, a process that releases heat and could potentially drive geological activity. All of this paints a picture of a planet that's still alive, in a geological sense, not as dynamic as Earth, but not frozen in time either. Mars is cooling, contracting, adjusting, and every so often, it shakes. If Mars once had an ocean, where was its coastline? In 1987, planetary scientist John Brandenburg proposed the existence of a primordial Martian ocean he called Paleo-Ocean, or Oceanus Borealis. He pointed to geographic features in the northern lowlands that resembled ancient shorelines boundaries that stretched for thousands of kilometers. Images from NASA's Viking orbiters revealed 2 possible shorelines near the pole, named Arabia and Deuteronilus. These features looked like the kind of boundaries you'd expect at the edge of a large body of water. But when scientists measured their elevations using NASA's Mars Orbiter Laser Altimeter in 1999, they found a problem. The shorelines weren't level. They rose and fell by several kilometers over thousands of kilometers of distance. On Earth, shorelines follow lines of constant gravitational potential. They're level because water always seeks the same height. If the Martian shorelines weren't level, they couldn't have been formed by a static ocean, or so it seemed. In 2007, researchers Taylor Perron and Michael Manga proposed a solution: true polar wander. True polar wander is what happens when a planet's rotation axis shifts relative to its crust. This can occur when large masses like the Tharsis volcanic region on Mars form and redistribute the planet's weight. The rotation axis adjusts to the new mass distribution, causing the planet to tip. When a planet tips, the centrifugal bulge at the equator shifts. The planet deforms, and any shorelines formed before the tipping event get warped as the crust adjusts. Perron and Manga's model showed that if Mars underwent true polar wander after its ocean formed, the ancient shorelines would have been deformed in exactly the way we observe today. The shorelines were level when they formed. They only became uneven after the planet tipped. This explanation fits, but it's not the only challenge. Some researchers argue that the supposed shorelines are actually volcanic deposits or wind-eroded features, not evidence of water at all. The debate continues. In 2016, scientists reported evidence of ancient tsunamis on Mars. 2 massive waves, triggered by asteroid impacts, swept across the northern ocean and left behind distinctive deposits. Lobes of debris containing boulders the size of cars, channels carved by retreating water, fields of ice blocks dropped in valleys. Numerical simulations showed that 30-kilometer wide impact craters would form in the Martian Ocean once every 30 million years. If the ocean lasted for even a few 100 million years, multiple tsunami events would have occurred. The tsunami deposits support the ocean hypothesis, but they also complicate it. Tsunamis would have erased or buried the original shorelines, making them even harder to identify. In 2022, researchers analyzing sediment data suggested that a large northern ocean existed on Mars, based on the distribution and characteristics of accumulated sediment in the lowlands. The patterns are consistent with long-term deposition in a marine environment. The evidence is mounting, but it's still not definitive. We know Mars had liquid water on its surface. We know it had lakes and rivers. We can see the deltas where rivers emptied into basins. 17 of those deltas are located at roughly the same elevation, exactly what you'd expect if they all formed at the edge of a large body of water. But proving the existence of a planet-wide ocean requires more than circumstantial evidence. It requires finding unambiguous markers, chemical signatures, sedimentary layers, or fossils that can only form in deep water. For now, we have a hypothesis. A strong hypothesis, supported by multiple lines of evidence, but not yet proof. In the northern lowlands of Mars, scattered across vast plains of dusty regolith, lie thousands of boulders. These aren't small rocks. They range from 0.5 meter to 2 meters in diameter, and they're everywhere. High-resolution images from NASA's Mars Reconnaissance Orbiter show boulder fields covering hundreds of square kilometers. In some locations, the density of boulders is so high that they appear to blanket the surface. The boulders are part of a geological unit called the Vastitas Borealis Formation, which covers about 45% of the northern lowlands. The formation dates to the late Hesperian to early Amazonian period, roughly 3 to 3.5 billion years ago, and is contemporaneous with the formation of the giant outflow channels that carved through the Martian highlands. The question is, how did the boulders get there? One hypothesis is that they were ejected by meteorite impacts. Mars is covered in impact craters, and large impacts can throw rocks for hundreds of kilometers. But high-rise imagery shows impact-free boulder fields regions where there are no nearby craters that could have been the source. Another hypothesis suggests periglacial activity. Freeze-thaw cycles could have fractured rocks and created patterned ground containing boulders. But the Vastitas Borealis Formation is much older than the recent ice deposits in the northern lowlands. A third hypothesis involves mass transport events. Catastrophic underwater landslides. On Earth, submarine landslides, also called mass transport deposits, can move enormous volumes of sediment down continental slopes. These flows are triggered by earthquakes, volcanic eruptions, or simply the buildup of unstable sediment. They travel as dense slurries of mud, rock, and water, and they can transport boulders and even kilometer-scale blocks of intact rock. Researchers studying terrestrial submarine landslides have documented blocks hundreds of meters thick and several kilometers long, transported tens or even hundreds of kilometers from their source. These blocks show up clearly in seismic imaging data from offshore oil and gas exploration. The boulders in the Vastitas Borealis Formation have characteristics consistent with terrestrial mass transport deposits. They're randomly distributed. They're not associated with obvious impact craters. And they occur in a region that, if the ocean hypothesis is correct, would have been underwater during the Hesperian period. If Oceanus Borealis existed, then sediment from the giant outflow channels would have poured into the ocean, creating unstable slopes along the margins of the northern basin. These slopes could have collapsed in massive underwater landslides, carrying boulders and debris across the ocean floor. This explanation fits the data, but like the shoreline hypothesis, it's not definitive. The boulders remain a mystery, one of many on Mars. Mars has 2 moons, Phobos and Deimos. Both are small, irregularly shaped, and probably captured asteroids. Deimos is about 12.6 kilometers in diameter and orbits at a safe distance of 23,460 kilometers from Mars. But Phobos is different. Phobos is 22.2 kilometers across and orbits at just 9,377 kilometers above the Martian surface. It completes an orbit every 7 hours and 39 minutes faster than Mars rotates. This makes Phobos one of only 18 moons in the solar system whose orbital period is shorter than its planet's day. And Phobos is falling. Tidal forces between Mars and Phobos are causing the Moon's orbit to decay. Phobos is spiraling inward at a rate of about 2 centimeters per year. That doesn't sound like much, but it's enough. In 20 to 40 million years, Phobos will reach the Roche limit, the distance at which tidal forces will overcome the Moon's self-gravity and tear it apart. What happens next depends on Phobos's structure. If it were a solid, monolithic body, it might survive past the Roche limit and eventually impact Mars. But Phobos isn't solid, it's a rubble pile. Data from the European Space Agency's Mars Express orbiter show that Phobos has a density of just 1.9 grams per cubic centimeter, much lower than solid rock. The Moon is porous, probably containing large voids. It's barely holding together under its own weak gravity, and it's already showing signs of stress. Long, shallow grooves line the surface of Phobos, radiating from the side that constantly faces Mars. These grooves aren't cracks from ancient impacts, they're stretch marks. As Phobos gets closer to Mars, tidal forces deform the Moon. The outer layer of regolith, about 100 meters of loose, powdery material, is being pulled and stretched. The grooves are the visible manifestation of that stress. When Phobos reaches the Roche limit, the tidal forces will be strong enough to pull the Moon apart. The regolith layer will be stripped away first, spreading into a ring around Mars. The ring will be dark. Unlike Saturn's bright, icy rings, Mars's ring will be composed of carbon-rich dust and rock, the same material that makes up Phobos. It will be relatively narrow at first, but over time it will spread out, reaching down into the upper Martian atmosphere within a few million years. Eventually, the material will rain down onto the surface, creating a slow shower of meteors. The larger chunks of Phobos will fall as well, impacting Mars and creating chains of elongated craters along the equator. Mars will have a ring system for somewhere between 1 million and 100 million years, and then it will fade as the debris falls to the surface. Deimos will remain, alone, the last moon of Mars. This has probably happened before. Some planetary scientists think Mars once had more than 2 moons. Simulations suggest that earlier generations of moons spiraled inward, broke apart, and rained down on the surface. The pattern repeats on geological timescales. So when Phobos falls, it will be continuing a cycle that may be billions of years old. For all that we've learned about Mars, there's one fundamental question we still can't answer with certainty. Was there ever life on Mars? We know Mars once had liquid water on its surface. We know it had a thicker atmosphere, a warmer climate, and environmental conditions that could have supported life. Lakes that lasted for millions of years, rivers that carved valleys, an ocean that may have covered 1/3 of the planet. In 2019, NASA's Perseverance rover drilled into a rock called Shiava Falls in Jezero Crater and extracted a sample called Sapphire Canyon. The sample contains features that may be biosignatures, chemical or physical signs of ancient microbial life. The rock has veins filled with organic compounds. It has small spherical structures that could be microfossils. It has chemical gradients consistent with metabolic activity. But it also has alternative explanations. The organic compounds could be from non-biological processes. The spherical structures could be mineral precipitates. The chemical gradients could be from thermal or hydrological activity. We can't say for certain. Not with the instruments we have on Mars. That's why NASA and ESA are planning a Mars sample return mission. Perseverance has collected 28 scientifically selected samples in sealed tubes. A future mission will retrieve those tubes and bring them back to Earth, where they can be analyzed in laboratories with instruments thousands of times more sensitive than anything we can send to Mars. Only then will we know. But even if Sapphire Canyon doesn't contain evidence of life, that doesn't mean life never existed on Mars. We've barely scratched the surface. Literally, most of the Martian surface remains unexplored. The subsurface remains almost entirely unknown. If life exists on Mars today, it's probably deep underground, living in fractures and pore spaces in the mid-crust, far from the toxic, radiation-soaked surface. We won't find it unless we drill, And if life existed on Mars billions of years ago, the evidence may have been erased by diagenesis, wind erosion, or cosmic radiation. Or it may simply be buried under kilometers of dust and rock, waiting to be found. The search continues. Mars is not what you think. It's not a dead world frozen in time. It's a planet that's still cooling, still shifting, still shaking with occasional marsquakes. It has a solid inner core crystallizing from a liquid outer core. It has tectonic stresses building and releasing in regions like Cerberus fossae. It's not a dry world. Deep beneath the surface, between 5.5 and 8 kilometers down, there may be an ocean's worth of liquid water trapped in fractured rock. On the surface, perchlorates in the soil can absorb moisture from the air and form brines that flow down slopes during the Martian summer. It's not red. The reddish dust is just a thin veneer, typically millimeters thick, coating a gray basaltic surface. The color comes from billions of years of chemical weathering and mechanical erosion, producing fine particles of iron oxide that hang suspended in the atmosphere and tint the sky butterscotch. It's not safe. The soil is toxic, contaminated with perchlorates at levels that would be dangerous to humans. The atmosphere provides almost no protection from cosmic radiation. The temperature swings from just above freezing at your feet to well below freezing at your head. And the dust storms can last for months, covering half the planet in a haze that blocks out the sunday. But it's also not impossible. NASA's Perseverance rover has demonstrated that Martian regolith contains accessible water. Engineers are working on systems to extract oxygen from the carbon dioxide atmosphere. Biologists have identified bacteria that can break down perchlorates and even use them as an energy source. Architects are designing habitats that could be built underground, shielded from radiation by layers of rock. Mars is hostile, but it's not insurmountable, and beneath the hostility lies a profound mystery. This planet was once like Earth. It had oceans, rivers, lakes, and possibly rain. It had a thick atmosphere and a protective magnetic field. It may have had life, and then, over hundreds of millions of years, it lost almost everything. The magnetic field collapsed, the atmosphere was stripped away, the water froze or evaporated, the surface became a toxic, irradiated desert. Understanding what happened to Mars helps us understand what could happen to Earth. How fragile is a planetary atmosphere? How important is a magnetic field? What processes can transform a habitable world into a barren one? These are not academic questions. They're fundamental to understanding the long-term survival of any planet with life. Mars is a warning. But it's also a laboratory, a place where we can study planetary evolution, atmospheric loss, and the limits of habitability. And it's a mirror. When we look at Mars, we see a version of what Earth could become if conditions change, or what Earth once was, in its earliest days before life transformed the atmosphere. The more we study Mars, the more we learn about our own world. Right now, NASA's Perseverance rover is driving across the floor of Jezero crater, collecting samples. The Curiosity rover is climbing Mount Sharp, analyzing layers of sediment that span billions of years. The InSight lander has finished its mission, but the seismic data it collected will be analyzed for decades. And overhead, 8 spacecraft orbit Mars, imaging the surface, measuring the atmosphere, and mapping subsurface water ice. We've learned more about Mars in the past 20 years than in all of human history before that. And every answer raises new questions. Why did the magnetic field collapse? Was it inevitable, or could it have been prevented? How long did the oceans last? What was the climate like? Could life have arisen in those oceans? If it did, is it still there, hidden underground? We don't know yet, but we will. The samples Perseverance is collecting will come back to Earth in the 2030 seconds. Those samples will be studied in laboratories with instruments that can detect organic molecules at parts per trillion concentrations. They'll be able to identify isotopic signatures of biological processes. They'll be able to date minerals to within a few million years. If there's evidence of ancient life on Mars, we'll find it. And if we don't find it in those samples, we'll keep looking. Because Mars is huge. We've explored less than 1% of its surface, and we haven't even begun to explore the subsurface. The story of Mars is still being written. Every mission adds a chapter. Every discovery changes our understanding. Mars is not what you think. It's not what anyone thought. It's stranger, more complex, and more mysterious than we imagined. And that's exactly why we keep going back.